1350 amp fuse is being used with a calculated ampacity of 1140 amps. There are several reasons why a fuse with a higher amperage rating than the calculated ampacity might be chosen. Firstly, safety margin. Fuses are often rated for a slightly higher amperage than the expected continuous load to provide a safety margin. This ensures that the fuse does not blow prematurely due to minor fluctuations in the load or ambient temperature changes. In this scenario, the calculated ampacity is 1140 amps, and the 1350 amp fuse provides a 210 amp safety margin. This represents approximately an 18% margin above the calculated ampacity. Secondly, transient currents. Electrical systems can experience transient currents, which are short-duration current spikes during startup or under fault conditions. These transient currents can be significantly higher than the steady-state operating current. A fuse rated precisely at the calculated ampacity might not be able to withstand these transient currents and could blow unnecessarily, causing nuisance trips. A higher rated fuse can tolerate these transient currents without interrupting the circuit. Thirdly, code requirements. Electrical codes and standards, such as the National Electrical Code, often have specific requirements for fuse sizing based on the type of load, conductor ampacity, and application. These codes may mandate that the fuse be rated at a certain percentage above the calculated ampacity, especially for motor circuits or systems with high inrush current or poor power factor. It's essential to consult the relevant electrical codes to ensure compliance and proper fuse selection. Fourthly, protection for other equipment. The fuse is not solely protecting the conductors. It's also protecting downstream equipment, such as switchgear, transformers, and other connected devices. A fuse rated precisely at the conductor ampacity may not provide adequate protection for this equipment during abnormal conditions, such as overloads or short circuits. A slightly higher rated fuse can offer a better balance between conductor protection and equipment protection. Fifthly, future expansion. If there is a possibility of future load increases or system modifications, using a fuse with a high rating allows for some flexibility without requiring an immediate fuse replacement. This can save time and money in the long run by accommodating potential load growth without compromising safety. It is imperative that the conductors are appropriately sized for the increased load in the future. Keep in mind the ampacity of the conductors must be rated to handle the increased current. In summary, while the calculated ampacity of the conductors might be 1140 amps, the 1350 amp fuse is used to provide a safety margin, account for transient currents, comply with code requirements, protect downstream equipment, and allow for future expansion. It is crucial to consider all these factors when selecting the appropriate fuse size for a given application. Always consult with a qualified electrical engineer or electrician to ensure proper fuse selection and compliance with all applicable codes and standards. In electrical systems, the selection of fuses is critical for ensuring safety, reliability, and protection of equipment and personnel. Understanding the various factors that influence fuse sizing is essential for making informed decisions and preventing potential hazards. Let's delve deeper into some of these factors. When calculating the ampacity of conductors, several factors come into play, including the conductor material, insulation type, ambient temperature, and number of conductors bundled together. The National Electrical Code, or NEC, provides tables and guidelines for determining the allowable ampacity of conductors under various conditions. For example, NEC Table 310.15 specifies the ampacity of insulated conductors rated up to 2000 volts. Based on the insulation type and conductor size. These ampacity values are based on specific temperature ratings for the insulation. If the ambient temperature exceeds the temperature rating of the insulation, a diluting factor must be applied to reduce the allowable ampacity of the conductor. In addition to ambient temperature, the number of conductors bundled together in a raceway or cable can also affect their ampacity. When multiple conductors are bundled together, they generate heat, which can raise the temperature of the conductors and reduce their ampacity. NEC Table 310.15 provides adjustment factors for conductor ampacity based on the number of current-carrying conductors in a raceway or cable. Transient currents, also known as inrush currents or surge currents, are short-duration current spikes that occur when electrical equipment is first energized or when there is a sudden change in the load. These transient currents can be several times higher than the steady-state operating current of the equipment. For example, motors, transformers, and capacitors typically draw high inrush currents when they are initially energized. Fuses must be able to withstand these transient currents without blowing unnecessarily. Time delay fuses, also known as dual-element fuses, are designed to tolerate transient currents without interrupting the circuit. These fuses have a built-in time delay mechanism that allows them to withstand short-duration overloads without tripping. Time delay fuses are commonly used in motor circuits and other applications where transient currents are expected. Electrical codes and standards play a crucial role in ensuring the safety and reliability of electrical systems. These codes provide guidelines for the design, installation, and maintenance of electrical systems, including fuse sizing. The National Electrical Code, or NEC, is the most widely adopted electrical code in the United States. The NEC contains detailed requirements for fuse sizing based on the type of load, conductor ampacity, and application. For example, NEC Section 430.52 specifies the maximum fuse size for motor circuits based on the motor's full load current and service factor. Electrical codes also address the protection of downstream equipment, such as switchgear, transformers, and other connected devices. Fuses must be selected to provide adequate protection for this equipment during abnormal conditions such as overloads or short circuits. The interrupting rating of a fuse is the maximum amount of fault current that the fuse can safely interrupt without failing. It is essential to select fuses with an interrupting rating that is equal to or greater than the available fault current at the point of installation. Available fault current is the amount of current that would flow in a circuit during a short circuit condition. It depends on the impedance of the power source, the impedance of the conductors, and the impedance of the equipment connected to the circuit. A short circuit study is typically performed to determine the available fault current at various points in an electrical system. This study helps engineers select fuses with appropriate interrupting ratings to ensure that they can safely interrupt fault currents without causing damage to equipment or injury to personnel. In addition to providing overcurrent protection, fuses also play a role in coordinating the operation of different protective devices in an electrical system. Selective coordination is a technique used to ensure that only the protective device closest to a fault will trip, while other upstream devices remain in service. This minimizes the extent of the outage and allows the rest of the system to continue operating. Selective coordination is achieved by carefully selecting the time current characteristics of the fuses and circuit breakers in the system. The time current characteristic of a fuse is a graph that shows the time it takes for the fuse to trip at various levels of overcurrent. By coordinating the time current characteristics of different fuses, engineers can ensure that the fuse closest to the fault will trip first, isolating the fault and preventing it from spreading to other parts of the system. Fuse selection is not a one-size-fits-all process. It requires careful consideration of various factors, including conductor ampacity, transient currents, code requirements, equipment protection, and future expansion. It is essential to consult with a qualified electrical engineer or electrician to ensure proper fuse selection and compliance with all applicable codes and standards. Regularly inspect and test fuses to ensure that they are in good working condition. Replace any fuses that are damaged, corroded, or have reached the end of their service life. Keeping your electrical system safe and reliable requires proper maintenance and attention to detail. Remember, electrical work can be dangerous. Always follow safety precautions and consult with a qualified professional when working with electrical systems. Proper fuse selection and maintenance are essential for ensuring the safety, reliability, and protection of electrical systems. By understanding the various factors that influence fuse sizing and following best practices for fuse maintenance, you can minimize the risk of electrical hazards and keep your electrical system operating smoothly. Always prioritize safety and consult with qualified professionals when working with electrical systems. The NEC, specifically Article 240, provides comprehensive guidelines for overcurrent protection, including fuse selection. This article covers topics such as the purpose of overcurrent protection, types of overcurrent devices, conductor protection, and specific requirements for different types of circuits and equipment. NEC Section 240.4 addresses the protection of conductors. It states that conductors must be protected against overcurrent in accordance with their ampacities. The overcurrent protection device, such as a fuse or circuit breaker, must be sized to protect the conductor from overheating and potential damage. NEC Section 240.6 covers the standard ampere ratings for fuses and circuit breakers. This section lists the available standard ratings for overcurrent devices, which are typically in increments of 1 amp, 3 amps, 6 amps, 10 amps, 15 amps, 20 amps, 25 amps, 30 amps, 35 amps, 40 amps, 45 amps, 50 amps, 60 amps, 70 amps, 80 amps, 90 amps, 100 amps, 110 amps, 125 amps, 150 amps, 175 amps, 200 amps, 225 amps, 250 amps, 300 amps, 350 amps, 400 amps, 450 amps, 500 amps, 600 amps, 700 amps, 800 amps, 1000 amps, 1200 amps, 1600 amps, 2000 amps, 2500 amps, 3000 amps, 4000 amps, 5000 amps, and 6000 amps. When selecting a fuse or circuit breaker, it is important to choose the standard rating that is closest to, but not greater than, the allowable ampacity of the conductor being protected. NEC Section 240.100 provides specific requirements for overcurrent protection of conductors 1000 volts or less. This section addresses topics such as conductor ampacity, overcurrent device location, and specific requirements for different types of circuits and equipment. NEC Section 430 covers the requirements for motor circuits and motor protection. This article provides detailed guidelines for sizing fuses and circuit breakers for motor circuits, taking into account factors such as the motor's full load current, service factor, and starting current. Motor circuits typically require time delay fuses or inverse time circuit breakers to accommodate the high inrush currents that occur when motors are started. NEC Section 450 addresses the installation and protection of transformers. This article provides requirements for overcurrent protection of transformers, taking into account factors such as the transformer's primary and secondary voltage, kVA rating, and impedance. Transformers typically require overcurrent protection on both the primary and secondary sides to protect against overloads and short circuits. In addition to the NEC, other industry standards, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA, provide guidance on fuse selection and application. These standards offer detailed information on fuse characteristics, performance, and testing. When selecting fuses, it is important to consider the specific application and the characteristics of the load being protected. Factors such as the type of load, operating voltage, available fault current, and ambient temperature can all influence fuse selection. There are different types of fuses available, each with its own unique characteristics and applications. Some common types of fuses include cartridge fuses, blade fuses, plug fuses, and current-limiting fuses. Cartridge fuses are cylindrical fuses that are commonly used in industrial and commercial applications. They are available in a wide range of ampere ratings and voltage ratings. Blade fuses are flat fuses with blade-like terminals that are commonly used in automotive and electronic applications. They are typically smaller and less expensive than cartridge fuses. Plug fuses are screw-in fuses that are commonly used in residential applications. They are designed to protect branch circuits from overloads and short circuits. Current-limiting fuses are fuses that are designed to rapidly interrupt high fault currents. They are commonly used in applications where high fault currents are possible, such as in industrial power distribution systems. Proper fuse installation is essential for ensuring the safety and reliability of electrical systems. Fuses should be installed in accordance with the manufacturer's instructions and all applicable codes and standards. Fuses should be installed in fuse holders or fuse blocks that are properly rated for the voltage and current of the circuit. Fuse holders and fuse blocks should be clean and free of corrosion. Fuse holders and fuse blocks should be properly secured to prevent them from coming loose or vibrating. Regularly inspect fuses and fuse holders to ensure that they are in good working condition. Look for signs of damage, corrosion, or overheating. Replace any fuses that are blown, damaged, or corroded. Replace any fuse holders that are damaged or corroded. Keep spare fuses on hand so that you can quickly replace a blown fuse. When replacing a fuse, always use a fuse with the same ampere rating and voltage rating as the original fuse. Using a fuse with a higher ampere rating can overload the circuit and cause a fire. Using a fuse with a lower ampere rating can cause nuisance tripping. Always disconnect power to the circuit before replacing a fuse. Use insulated tools to avoid electric shock. Wear safety glasses to protect your eyes. Electrical safety is paramount when working with electrical systems. Always follow safety precautions and consult with a qualified professional when working with electrical systems. To energize circuits before working on them, use insulated tools and equipment. Wear appropriate personal protective equipment. Be aware of potential hazards and take steps to mitigate them. Proper fuse selection, installation, and maintenance are essential for ensuring the safety and reliability of electrical systems. By following best practices and consulting with qualified professionals, you can minimize the risk of electrical hazards and keep your electrical system operating smoothly.